So when you go up to that scale facility, the real first thing that breaks is the process. And what that means is all the ways you go about doing your layout out on site. And that starts with how you set your reference points, how many you need. At that scale, there's way more reference points that you need. They all have to tie into each other exactly. Otherwise, they're starting from a bad place. Then when you actually go to perform the work, perform the layout, chaining measurements together, all those individual tolerances on a single measurement, they just keep compounding and stacking up. And all you get is way out of tolerance by the end of that measurement chain. That just doesn't exist at the smaller scale because you're only measuring once. And then finally, you can't really easily measure back to your origin as you get to this scale. So when you perform all these measurements, you get to this end state at the very end, and you can't check to make sure that you're still tied in properly to that first reference point because it might be 800 feet away and you just simply can't measure that. Yeah, so the problem is it's not just more work. If you go to a larger area, it's not just, I need to do a little bit more work. It is all of those methods very quickly fall apart that just work naturally at a smaller scale. And an easy way to think about this, an easy example might be in a small building, you can maybe just set one baseline off a set of columns, and you set one baseline running north-south, one baseline running east-west, and you can pull measurements all day and finish your project off just those single baselines. No problem at all. As you start growing in scale, you just simply can't measure far enough anymore. Nobody makes a 1,000-foot tape measure. And if they did, a 1,000-foot tape measure is not going to be an accurate way to set those measurements. So now you have to measure off multiple baselines. You have to chain measurements together. The same manner, more sophisticated players might run survey crews with total stations and use more sophisticated, accurate measurements at scale. That starts to create a different problem, though, because you end up with just the throughput of how much that crew can work. The density goes so high that they might be on site for months, 6 months, 8 months, just to achieve the amount of points they have to do at that scale. So we actually run into this a lot with our customers in automated warehousing and distribution centers that are laying out robotic workstations, AMRs. They start as a smaller company. They have a lot of success at the small scale with a single engineer who knows how to lay out the system. And they go out for a few weeks and measure where the AMR stickers go and measure how the robotic workstation gets installed. Potentially, they even buy a laser scanner and they spend $80,000 or $100,000 to get something really accurate, and that one person knows how to use it. But then as the company starts to have success and grow, they have suddenly a contract for 10 sites at 10 times the size, and that single engineer is now overwhelmed on being able to go out and do that amount of work. Potentially, the company could hire more people. They could hire larger workforce. They could go buy a bunch more laser scanners. But now they're putting all their bets on that scope will continue, that they'll continue to get those contracts, and they're starting to carry more and more of a utilization risk, in addition to having to deeply train a workforce. On the flip side, we can carry a lot of that utilization risk because we can mobilize however many robots we need, and we can mobilize across the country as the deep experts in performing this layout and do that on a per project basis. Yeah, so everybody's instinct is you have a bigger project, just get more people, problem solved, right? The problem with that is productivity, accuracy, all the things that you need don't just scale with workforce. And in fact, 2 times the number of people don't equal 2 times the amount of work done. You start having more and more coordination overhead, differences in how people perform the work that start to bleed into how successful it is. And you have multiple references getting used. When you swarm a bunch of people, not everyone is going to be using that same baseline anymore. And so now measurements are coming from all different directions, and it's just getting more and more cluttered out on the field. In addition, geographically, when you scale across the country, that's a whole nother set of issues because labor markets across the country have different levels of skill, different availability. Many of our customers building complex data centers are building in places that don't have a strong local population. There's just not a lot of people that live around where these data centers are going on. So the local labor just to staff these projects doesn't really even exist because there aren't people there who have any of that experience. Finally, in addition, in a small scale, in a 50,000 square foot project, a 30,000 square foot project, a single exceptional person can carry the entire project and drive that success. As that scale goes up with the size of project or the number of projects, the geographic scale, it's really hard to find that many exceptional people. And you even get to a point where the projects get so large that one person can't just feasibly have an impact. So we see in data centers, it's a very dense environment. And so you might be thinking that, okay, I just have a bunch of measurements I have to make and I can do one after the other. Easy, right? Because it's really dense. The problem is we get into just ridiculous levels of scale where a single trade in a large data center might be looking to lay out 60 or 70,000 points. And good survey crews, good field engineers, they'll tell you, yeah, I can do 500 points in a day. And they're probably right. They might be able to do 500 points in a day. The problem becomes, can they do 500 points a day for 120 days straight to get to 60,000 points? And most likely, they're not going to be able to. They're going to hit a wall. The productivity is going to slow down. That is incredibly hard to do every day for 120 days at that peak production rate. So what we see is that density creates a real throughput challenge of just how productive can your crews be and how long is that work going to take? Because everyone still has to be measured precisely. In the warehouse setting, on the flip side, especially if it's more open, you're still dealing with scale. You're still dealing with large distances. So maybe the density might not be there, but the difficulty of performing each individual measurement goes up. And that's where our robotic solution can really help because at that density scale, when you're doing 60,000 points, the robot doesn't get tired. The robot just keeps printing and just keeps performing its task. And at the long distances, when you're in the warehouse environment, it's just as accurate after driving 100 feet as it is if it's driving only 5 feet. So it's able to hold that accuracy over those distances or hold that speed during highly dense, highly repetitive tasks. So the first thing I tell them is just because their processes work at the 80,000 square foot level doesn't mean it's going to work as they grow larger and larger, right? That is a risk to think that because it's worked small, it's going to keep working big. Because as we've talked about in some of these other discussions, the compounding error, the fact that you just keep chaining measurements and that tolerance, that individual measurement just keeps growing. The fact that you're now dealing with reference geometry and control points that are spread much further apart or many more that you're having to reference and single baselines fall apart. All of those things, in addition to the difficulties and just even staffing a project with the right number of qualified people to do that work, become more and more difficult and grow exponentially in what it takes to go and execute that project. And before you even get out into the field, one of the big things we see, even just scaling your VDC process, scaling the model delivery, that's a whole nother area where risk can live in to going and delivering the project successfully. We've got a VDC team that is working at the largest project types across the entire country. And we see industry-wide that scale. We don't just see it at one project type or one growing data center class within a general contractor. We see that industry-wide, and we're able to absorb that model processing and that coordination risk by the way that we're just looking at models as we do that processing. We take that CAD model from the customer, we process it, we look at it deeply to understand how the layout's going to work, and often we're finding coordination busts, and we're working with our customers' EDC teams to rectify those situations, whether it might be a trapeze that pokes through the drywall or two different trades intersecting, or even in an automated warehouse recently, we were 4 days away from a very complicated retrofit project that was about to kick off with a customer. And we caught that an old hardware block was being used in their AutoCAD drawing. We would have potentially laid that out, or anybody would have laid that out. And weeks later, while they're trying to retrofit a live facility, the project would have ground to a halt because they wouldn't physically be able to install the newer version and the newer revision of this hardware. It just simply wouldn't have worked. But because we've got this VDC team that's always looking at this scale, we're used to dealing with all these common pitfalls and have a really good checklist that we can run through as we're converting the models into layout for the robot. Additionally, automated layout has one vulnerability, really, and that is still the control network. Just like any other layout, control and really bad control can still set layout off, right? If you have bad reference points in the field, it doesn't matter whether you're using a tape measure, a total station, or robotic layout. If your reference points aren't good, you're just simply not going to put your system in the right place. However, because we're working at this scale, we are commonly working with control networks in million square foot buildings. We understand how to use our robot to analyze that control network, verify that the control is sufficient and it is accurately placed. And we have that all built into our system so that we can show up, understand control's good, and immediately start to execute and know that we're going to be putting that layout in the right spot. A big challenge in layout in general, and this applies at small scales as well as large scale, and just really gets amplified at large scales, is the quality of your reference points, your control points. How are you positioning yourself and the systems you're laying out in the building? At small scale, a lot of times you can get away with checking one column line and setting an offset, one baseline, and then go perpendicular to that, go north-south, check another column line, place an offset line. That's your baseline. And in the small buildings, you can just take all your measurements from those two baselines and you've got a pretty strong set of layout. The problem becomes when you move to the larger scales, you simply can't do that anymore, especially if you're using something like tape measure. They just don't make tape measures long enough to do that. So now you're chaining measurements together. Not only that, but at the super long lengths of a tape measure, temperature starts to matter. The tape measure is growing and shrinking based on the temperature. And then if you take 3 or 4 consecutive measurements off of that, you've just baked in that temperature change to every single measurement. Not only that, if the baseline is at all crooked, if it's skewed a little bit, you have a lever arm problem where you might be 500 feet away and a small angle has now really compounded into a large distance. Your system that you're laying out is now off. So you've increased the source of error substantially with all these different methods, just because now you're working at such a large scale. Another problem we see, even with sophisticated methods, using a total station, field engineers, surveyors, or trades running them out in the field, is that at the larger scales, the number of control points you're using, the number of discrete sections that you need to do and set up in, because sight lines just, you can't see that far, right? There's material, there's pallets, there might be a demising wall that's been built. Now you are creating a bunch of different sub-control networks, and understanding whether or not you still have a tight set of control points and you still have quality resections becomes more and more difficult. And you start operating at these subscales, but at this very large building. And what you end up with is 20 different layouts all around the building that don't actually match up. One of the things that we do when we get in the field with our robot is verify the control network that's been set on the site. And so our robot will measure all the control points it can see and understand the quality of that control network and how well the points tie into each other and whether there's any disjoints. We've been on some very large projects, 800, 900,000 square foot slabs, where we have found 1 to 2 inch control busts between different sets of control, where the surveyor, the field engineer, when they set control, had a bump total station, had something go wrong during that process, maybe between 2 different setups. And if you blindly trust those reference points, because you can't really see that much at that scale, right? You're not able to back check all the way to an origin effectively. If you blindly trust some of those reference points out there, you end up baking that joint right into your layout and right into your building. And the problem is that really shows up once things start getting installed. If everyone is using that control point, everything looks good. No trades are clashing, no systems are clashing. But then when you go to turn the facility on or you go to do any of your final checkouts, that's when those type of things start to show up. And that costs way more money to fix than if you're detecting it when the robot first shows up on the site and it's a simple email and maybe a surveyor remobilizing to correct a control network.